We are about 23 minutes away from the planned liftoff of a Falcon 9 rocket from the coast of Florida. The mission? To fly much-needed astronaut supplies and research experiments up to the International Space Station.
The International Space Station, a symbol of global collaboration and innovation, is nearing the end of its 30-year journey. By 2030, the 400-ton structure will be fully decommissioned, but that massive station can't just be left there. NASA and its international partners have laid out an ambitious plan to ensure its safe return to Earth. Key to this mission is minimizing risks to both the environment and human populations. SpaceX has been awarded a $1 billion contract to lead the deorbiting operations. And who's leading it all? Well, Elon Musk himself. That's who. But getting a whole space station back to Earth isn't the same as sending it up there in the first place. There's a lot more to it. In this video, we're going to bring you up to speed on it all. The International Space Station. The International Space Station stands as one of humanity's most remarkable achievements in space exploration. Its construction began in 1998 with the collaboration of 5 space agencies: NASA, United States; Roscosmos, Russia; ESA, European Space Agency; JAXA, Japan; and CSA, Canada. Over a span of more than a decade, the assembly of this $150 billion project involved over 40 assembly flights using space shuttles and Russian rockets. Modules, solar arrays, and intricate systems were painstakingly pieced together in orbit, creating the largest structure ever built in space. The ISS became operational in 2000, when the first long-duration crew arrived. Since then, it has been continuously inhabited, serving as a home for astronauts and cosmonauts from 20 countries. These individual countries have carried out scientific experiments, tested technologies, and inspired global audiences with their missions. The station's collaborative nature represents a milestone in international unity, showcasing how nations can work together to push the boundaries of human capability. The station's modular design allowed for incremental construction, with its first module, Zarya, launched in November 1998. This Russian-built module provided the initial propulsion and power capabilities. It was followed closely by the US-built Unity module, which served as the station's first connecting node. As more modules were added, including laboratories from Europe and Japan, the ISS grew into a fully operational research platform. Astronauts aboard the ISS have participated in numerous groundbreaking experiments, contributing to fields such as medicine, physics, and earth sciences. Highlights include testing microgravity's effects on the human body, observing phenomena like fluid dynamics and material behavior in space, and even studying climate change through detailed Earth observations. The station also played a critical role in fostering private sector involvement in space exploration, serving as a testing ground for commercial spacecraft like SpaceX's Dragon and Boeing's Starliner. Not just a lab. The ISS's importance cannot be overstated. As the largest human-made structure in orbit, it spans 357 feet end-to-end, roughly the size of a football field. It represents a union of advanced engineering, technological ingenuity, and political will. The station's construction and operation have brought together rival nations, particularly the United States and Russia, during times of geopolitical tension. This unprecedented collaboration has paved the way for future multinational space initiatives, proving that humanity can achieve extraordinary feats when working together. In addition to its scientific and political significance, the ISS has acted as a testing ground for technologies crucial to future missions to the Moon, Mars, and beyond. Its contributions to understanding life in space have informed spacecraft designs, habitats, and life support systems for deep space exploration. However, the ISS is slated for decommissioning by 2030, marking the end of its historic journey. Plans for its controlled descent are already in motion, and this didn't just come out of nowhere. A slow decline. The International Space Station is showing clear signs of its age after more than 2 decades in orbit. Central to its slow decline are the deteriorating structural and technical systems that can no longer meet the demands of sustained operation. One prominent example is the Zarya cargo module, the station's very first component, launched in 1998. Originally designed for a 15-year service life, Zarya has developed cracks in its hull, some of which have caused persistent air leaks. Maintaining cabin pressure has become an ongoing challenge, requiring constant monitoring and periodic repairs. These cracks point to fatigue in the station's materials due to prolonged exposure to the harsh conditions of space, including temperature extremes, micrometeoroid impacts, and radiation. Beyond Zarya, a staggering 80% of Russian-made systems on the ISS, like life support units, electrical panels, and thermal regulators, have exceeded their expected lifespan. For instance, the Electron system, which produces oxygen for the crew, has seen frequent breakdowns, necessitating backups and regular maintenance. Additionally, the Vozduk CO2 scrubbers and thermal cooling units operate at reduced efficiency, increasing the workload for station engineers and crew members tasked with keeping them functional. Failures in these critical systems could jeopardize the safety of those on board. The financial burden of maintaining the ISS has soared in response to its aging infrastructure. Annual costs to sustain operations hover around $3 billion, with much of that going toward repairing or replacing key components. For example, solar arrays, essential for generating power, have suffered from prolonged wear. Their efficiency has declined due to physical degradation and accumulated dust, necessitating costly upgrades or replacements. Furthermore, many of the ISS's early components are no longer in production, meaning replacement parts often require custom fabrication. This has led to longer timelines for repairs and higher expenses. Additional signs of decline are evident in modules added later to the station, including Russian-built docking compartments and US-built laboratory spaces, which now show micro-cracks and insulation wear. These issues not only compromise their functionality, but also raise concerns about the integrity of the station as a whole. As the station ages, it demands increasingly frequent and elaborate repairs, drawing into question the practicality of extending its operations and making decommissioning a financially and technically prudent choice. Political and operational challenges. The ISS has long been hailed as a beacon of international collaboration in space exploration. However, growing geopolitical tensions have strained the partnerships that are critical to its operation, especially between the United States and Russia. Roscosmos, the Russian space agency, has signaled its intention to withdraw from the ISS program by 2028, citing both technical and political factors. This decision is heavily influenced by the fallout from the Ukraine conflict and escalating sanctions, which have complicated Russia's broader international engagements. Adding to the uncertainty, Russia has announced plans to focus on developing its own orbital station, suggesting a pivot away from cooperative efforts like the ISS. Since Russian-built modules are integral to key operations, most notably propulsion systems used to stabilize and adjust the station's orbit, their departure would leave significant gaps in the ISS's functionality. The challenge of achieving consensus among the ISS's 15 partner nations on its future operations has also emerged as a critical hurdle. The United States, a primary financier of the station, is shifting its focus to more ambitious projects, such as lunar missions through NASA's Artemis program and collaborations with private companies for commercial space habitats. Japan has expressed similar interest in pursuing new exploratory ventures beyond Earth orbit. This redirection of resources makes it increasingly difficult for countries to justify the high costs associated with maintaining and operating the ISS, especially as its infrastructure ages and requires more substantial investment. Operational disagreements further complicate matters, particularly around funding, access, and future ownership of shared technologies. Rising costs of maintenance, which disproportionately fall on major contributors like the US, have led to questions about equitable financial contributions from smaller partners. There have also been tensions regarding the allocation of research opportunities on the station. Countries like Europe, Japan, and Canada aim to maximize their use of laboratory modules, often competing with NASA and Roscosmos for access. This whole situation is simply way too complicated here. But let's not forget, the space station being in space isn't exactly a cakewalk either. Threats from space debris. Space debris poses one of the most pressing risks to the ISS. It orbits Earth at approximately 28,000 kilometers per hour, and at such speeds, even tiny fragments of debris have the potential to cause catastrophic damage. The growing number of objects in low Earth orbit, estimated at over 36,500 pieces larger than 10 centimeters, makes the hazard here a lot worse. These include defunct satellites, fragments from collisions, and remnants of rocket stages, all of which remain in orbit for extended periods. NASA and other monitoring organizations track this debris constantly, but close calls have become increasingly common. Over the station's operational life, dozens of emergency maneuvers have been executed to avoid potential collisions. Each maneuver drains valuable fuel and disrupts the station's operational schedule, highlighting both the immediate dangers and the logistical challenges of continuing ISS operations. A catastrophic scenario known as Kessler syndrome looms over this growing threat. This chain reaction occurs when an initial collision between objects in orbit produces a cascade of debris, which then collides with other satellites and spacecraft, exponentially compounding the danger. If such a cascade were to happen, LEO could become a chaotic, hazardous zone, potentially rendering the region unusable for decades. The risk of Kessler syndrome has escalated significantly in recent years due to events like the deliberate destruction of satellites during anti-satellite weapon tests by several nations, as well as accidental satellite collisions. These incidents contribute thousands of debris fragments into orbital paths that intersect with the ISS's trajectory. Studies indicate a 30% increase in the likelihood of debris impact on the station compared to a decade ago, showing us the real gravity of the issue. Compounding the problem are the technical challenges involved in avoiding debris. The ISS relies on its aging Russian-built propulsion systems for collision avoidance, which perform complex thruster adjustments to alter the station's orbit temporarily. However, these systems, much like other components on the ISS, are nearing obsolescence and becoming less reliable. Moreover, fuel limitations make every maneuver a delicate balance between safety and sustainability. The station's long-term viability depends on mitigating debris risks, yet as the hazards continue to multiply, the prospect of safe operations diminishes. The growing space debris crisis is a significant factor driving the decision to decommission the ISS by 2030, but this is where the real work begins. The plan for deorbiting decommissioning. The ISS is a massive task that involves careful planning, innovative technology, and significant collaboration. The primary objective is to bring the station back to Earth in a safe, controlled manner, minimizing both the environmental impact and the risk to human lives. SpaceX, having already proven its capabilities with reusable spacecraft, was awarded a $1 billion contract for this deorbiting mission. The company will leverage its expertise and resources to orchestrate the gradual removal of the ISS from orbit, a process that will unfold over several years. A key part of SpaceX's mission is the development of a modified Dragon capsule, which will act as a towing tug to pull the ISS into a controlled descent. Unlike traditional methods that might involve using the station's own thrusters for this purpose, SpaceX's capsule will provide the necessary propulsion, gently lowering the ISS's orbit step by step. SpaceX's technological capability to attach a spacecraft to the ISS, redirect its trajectory, and manage controlled deorbiting represents a first in space station disposal techniques. The towing tug will be responsible for maintaining precise control of the station's trajectory during the critical descent period, ensuring that the ISS deorbits into a designated graveyard orbit, or eventually into Earth's atmosphere over a remote area, like the South Pacific Ocean, to minimize any risk to human settlements, but it can't happen all at once. Decommissioning timeline. The deorbiting process will begin as early as 2026, marking the first phase of a gradual descent. Starting at a standard operational altitude of around 400 kilometers, the ISS will slowly lower its altitude to 320 kilometers, leveraging the controlled propulsion from SpaceX's Dragon capsule. This lowering will not be sudden, but rather a series of careful adjustments designed to give engineers full control over the station's trajectory. One of the critical milestones in the timeline is the evacuation of the crew. Approximately 6 months before the ISS reaches its designated re-entry altitude, the crew will be evacuated, and all operations aboard will be brought to a halt. This ensures the safety of the astronauts, as the risks involved with re-entry can be dangerous for any remaining crew members. Once the station has descended to 220 kilometers above the Earth's surface, atmospheric drag will take over, pulling the ISS towards its final, fiery end. At this altitude, the natural resistance from the thin layers of the atmosphere will begin to hasten the descent, with the ISS breaking apart and burning up as it enters denser layers. The gradual lowering and controlled approach ensure that the debris that survives re-entry will fall into the remote regions of the Pacific Ocean, an area devoid of shipping lanes or significant human populations. The primary goal of the deorbiting operation is to avoid the uncontrolled crashes that have occurred with other space stations and debris-laden objects in the past, such as China's 2007 test with its Long March missile. These uncontrolled incidents pose serious risks, as fragments of space debris can crash into populated areas, causing considerable damage or loss of life. Therefore, a major aspect of the ISS deorbiting mission will be careful monitoring and piloting during re-entry to guide the debris over a safe, uninhabited zone. The controlled re-entry is intended to eliminate any hazards associated with the station's remains. SpaceX's ability to monitor and adjust the descent trajectory will allow the ISS to safely burn up in the atmosphere or fall into the ocean with minimal impact. But there are still risks. Challenges and risks in execution. Deorbiting the ISS presents an array of technical and environmental challenges. Despite careful planning and innovative technology, the process of safely deorbiting a 400-ton space station is fraught with variables that could complicate its successful completion. Among these challenges are unpredictable atmospheric forces and the potential environmental impact of the station's remains. One of the most significant challenges in deorbiting the ISS lies in managing the atmospheric drag that will drive its descent. Drag is not a constant force, and its intensity can fluctuate, influenced by a number of external factors, such as solar activity and atmospheric density. For example, when the Sun experiences periods of heightened activity, like solar flares or coronal mass ejections, the increased solar radiation can cause the Earth's upper atmosphere to expand. This leads to a greater density at high altitudes and, consequently, greater drag on orbiting objects, including the ISS. The drag factor can then change unexpectedly, making it more difficult to control the timing of the descent and the path it takes toward Earth. SpaceX will need to monitor these atmospheric changes continuously. If solar activity spikes, the impact on drag could cause the ISS to descend too quickly or unpredictably, requiring rapid adjustments from the towing system to prevent deviation from the planned path. Conversely, low solar activity could result in less atmospheric drag, which may slow the ISS's descent, delaying re-entry. Therefore, it's essential to track and predict these changes, with adjustments made in real time to ensure a smooth deorbiting process. Along with the technical hurdles, the environmental risks posed by the deorbiting process must not be overlooked. The ISS contains several hazardous materials that, if mishandled or exposed, could have detrimental effects on Earth's ecosystem. Perhaps the most concerning of these are toxic substances such as hydrazine, a propellant used in the station's thrusters, and radioactive materials housed in its batteries and other components. These materials pose considerable risks if they are released into the atmosphere or the ocean during re-entry. A primary worry is the potential leakage of such substances into the Pacific Ocean, where the ISS's debris is scheduled to fall. While the controlled re-entry plan ensures that most of the station will burn up upon re-entry, some remnants might survive, including parts with hazardous materials. The station's location over an uninhabited region of the ocean minimizes the risk of human exposure, but marine ecosystems could still be affected by toxic substances in the materials that survive re-entry. Researchers and environmental agencies must therefore plan for the worst-case scenario, ensuring that waste management protocols are in place if any dangerous debris is not fully vaporized upon descent. Additional environmental considerations include the potential long-term ecological effects if space debris discharges any particles into the ocean, whether through propulsion waste, battery remnants, or other station components. This risk underscores the importance of thorough testing and constant oversight during the deorbiting and disposal phases. These challenges, ranging from the unpredictable nature of atmospheric drag to the environmental threats posed by toxic materials, require comprehensive management strategies, including advanced prediction systems and robust containment measures for any dangerous remnants that might survive re-entry. Success depends on staying ahead of these risks while keeping the plan adaptable to ensure the ISS is deorbited safely and with minimal environmental harm. The endgame at Point Nemo. The final destination for the decommissioned ISS is set at a remote location known as Point Nemo, situated in the South Pacific Ocean, more than 2,700 kilometers from the nearest land. This vast expanse, far from human habitation, has become the go-to space graveyard for defunct satellites and spacecraft. Over 100 missions have been deorbited into this zone, making it an ideal choice for safely disposing of the ISS. Why Point Nemo? Elon Musk's SpaceX will play a critical role in making this complex transition as smooth and safe as possible. Point Nemo, located in the vast expanse of the South Pacific, is ideal for such an operation due to its seclusion and lack of human presence. The area has served as a spacecraft cemetery for many missions before, including Russia's Mir space station in 2001. Musk's company's advanced capabilities make the task of guiding the ISS toward this remote point, where the risk of harming humans is minimized, a realistic and reliable solution. SpaceX's participation showcases how commercial space companies like Musk's have become indispensable to such massive operations, bringing their innovative approach and significant resources to government-led initiatives. As the ISS descends from its 400-kilometer orbit towards Earth, friction from the atmosphere will cause much of its components to burn up. However, thanks to the precision and expertise of SpaceX's engineers, the station's descent will be managed in a highly controlled manner to ensure the maximum safety of both the station's remaining components and Earth below. Most of the ISS will disintegrate during re-entry, but more resilient structural parts, such as the station's trusses, will likely survive the fiery journey and hit the ocean intact. This precision, brought to life through SpaceX's state-of-the-art technology, underscores the growing role of private aerospace companies in supporting the space programs previously solely controlled by governments. Musk's relentless pursuit of technological advancement has led to a system that actively minimizes the risks involved in high-stakes space deorbit operations. After the ISS's disintegration, surviving debris will fall into the controlled zone near Point Nemo, spreading across an area approximately 1,500 kilometers by 100 kilometers. Given that Point Nemo is in the least inhabited part of the Earth's oceans, the plan is designed with minimal environmental disruption and risk to human life. Musk's team at SpaceX is ensuring that this final stage of the mission will minimize collateral damage or danger, reinforcing their commitment to both technological excellence and ecological responsibility. Lessons learned from previous space station decommissioning, like Skylab's failed re-entry in 1979, serve as a cautionary tale for this final operation. Musk's leadership in space exploration has transformed approaches like these, moving them from the realm of government projects to efficiently manage commercial endeavors with global cooperation and safety in mind. With this strategic partnership, the controlled re-entry of the ISS into the Pacific Ocean and the eventual deorbiting operation exemplify Musk's ongoing impact on space missions. From advancing reusable rocket technology to now guiding a major international space project to its final chapter, SpaceX is taking a central role in modernizing and ensuring the continued exploration of space, setting new benchmarks for safety, innovation, and environmental consideration. All of this isn't just regular plans on paper. Musk has had a lot to learn from. Lessons from Mir's decommissioning. Russia's Mir space station, which was deorbited in 2001, provides a significant precedent for the ISS deorbiting process. The complexities faced in guiding Mir safely back to Earth have offered valuable insights for ensuring a more controlled re-entry for the ISS. SpaceX, under Elon Musk's leadership, will leverage advanced technology and the lessons learned from Mir's deorbit mission to avoid some of the difficulties encountered back then. Mir's final descent involved unpredictable atmospheric drag, which resulted in some challenges in maintaining the proper trajectory for a safe re-entry. The station's unexpected descent speed fluctuations were dealt with through consistent monitoring and course adjustments as it neared Earth. This experience highlighted the importance of real-time atmospheric data and precise tracking for managing re-entry trajectories, lessons that SpaceX's engineering teams are incorporating to avoid similar issues for the ISS. Despite its successful deorbit and re-entry, Mir's decommissioning wasn't without complications. One of the biggest issues that arose was its final debris distribution. While the majority of Mir's components were burned up during re-entry, debris that survived caused significant concern. In particular, the debris field left behind could have resulted in harm if it had impacted populated areas. This was an issue mirrored during the 1979 Skylab re-entry, where parts of the space station fell over Western Australia, though fortunately with no significant damage. These incidents provided a critical lesson in the importance of accurately predicting and targeting the final debris field during a re-entry, particularly when aiming for a spacecraft cemetery like Point Nemo. The ISS deorbiting plans will carefully use data from previous missions to refine the targeting process to ensure minimal risk to human populations or environmental impact. For the ISS's deorbit, SpaceX's advanced guidance systems, combined with improved monitoring of atmospheric variables, will help reduce the risks of erratic re-entry paths. While the experiences from Mir's re-entry highlighted the challenges of atmospheric drag and debris distribution, they also paved the way for a more methodical, well-monitored approach to the deorbiting of large, aging space stations. Musk's company, benefiting from decades of advancements in space travel, is working hard to improve the precision of these operations to ensure that the lessons learned from Mir and Skylab deorbit failures result in a significantly safer mission for the ISS. This knowledge is also feeding into strategies to further protect the integrity of Earth's orbit for future spacecraft missions. But Elon Musk can't just do it all without any controversy, can he? Potential controversies and concerns. As the decommissioning of the ISS approaches, public skepticism surrounding the process is growing. One of the primary concerns is the potential environmental harm caused by the controlled re-entry. With the ISS scheduled to land near Point Nemo, a remote location in the Pacific Ocean, some worry about the long-term impacts on the ecosystem. The possibility of toxic materials like hydrazine and radioactive debris leaking into the ocean remains a contentious issue. Though SpaceX and NASA have carefully planned for these risks, including detailed mitigation strategies, the public remains understandably anxious about the potential consequences. These concerns are further amplified by geopolitical tensions, particularly with ongoing space projects from various international actors, including Russia and China, potentially complicating collaborative efforts in space exploration and debris management. Elon Musk's influence at SpaceX, with his ambitions for space colonization and ambitious commercial space ventures, raises questions about how these private sector-driven plans might prioritize safety versus technological and business interests. To alleviate public skepticism, NASA and SpaceX are focused on transparent reporting throughout the entire decommissioning process. Musk's SpaceX, which has earned significant trust due to the success of its reusable Falcon rockets and Dragon capsules, is using its proven track record in space travel to assure the public that ISS re-entry will be executed safely. Key steps include ensuring that only a small amount of debris, such as structural trusses, survives re-entry, and that it lands in a monitored low-risk zone near Point Nemo. Additionally, both NASA and SpaceX are working closely with global authorities to develop and execute contingency plans that address any potential mishaps in the deorbiting procedure. There are also backup options available to prevent debris from reaching populated areas in case of unforeseen circumstances. Clear communication and collaboration with other space agencies will be critical to ensure that any risks associated with the ISS's deorbit are proactively managed. Despite the comprehensive plans in place, there remains a palpable tension in the public's mind regarding the unknowns of a mass re-entry, especially when it involves a structure as massive as the ISS. However, NASA and SpaceX's dedication to maximizing safety and minimizing environmental consequences should, at the very least, offer some reassurance as we approach this historic event, but that's not the end of it. The ISS Replacement. Elon Musk's SpaceX is taking on an impressive array of transformative space projects that aim to not only redefine humanity's reach beyond Earth, but also to foster sustainable exploration in space. One of the company's flagship endeavors is Haven 2, a next-generation space station that will eventually supersede the ISS. Set to be significantly larger than its predecessor, Haven 1, this new space station will offer state-of-the-art facilities and labs tailored for advanced research, particularly in microgravity and in-space manufacturing. The space station will allow researchers to push the envelope on technologies that could revolutionize industries both in space and back on Earth. Haven 2 will also serve as a launchpad for private sector collaboration, where businesses can conduct experiments and manufacture products in the unique environment of microgravity, vital steps toward achieving Musk's broader goal of a multi-planetary civilization. The Haven 2 initiative is an ambitious part of SpaceX's overall mission to pave the way for a commercially driven space economy. With private space stations like Haven 2 becoming operational, the vision for space exploration shifts from government-funded projects to a more diverse range of commercial players, opening up access to orbital environments for companies in various sectors like manufacturing, pharmaceuticals, and technology. In that sense, Haven 2 is positioned to be a cornerstone in turning space into an economically productive and sustainable realm. This shift in space exploration could fundamentally change how space stations and missions are operated in the future, with companies like SpaceX providing the infrastructure for international and commercial cooperation. With the future-looking missions of Haven 2 and the safe removal of the ISS, SpaceX, under Musk's direction, is poised to become a major name in commercial space exploration, laying the foundation for the ambitious future that Musk himself envisions, making space travel commonplace and eventually turning Mars into a sustained home for humans. While that seemed like wishful thinking not long ago, it's now officially happening, and Musk is getting through it all one step at a time. The only question is, will it actually happen in the same timeline he thinks it will? What do you think? Leave your thoughts in the comments below, and if you like this video, don't forget to subscribe to our channel. See you in the next one.